Welcome to the closing remarks of AWS reInvent 2024. This is the closing ceremonies. So now that we have you all locked in for this ceremony, let me rant here for a little bit. Who is tired of walking? Who is tired of being lost and feeling like, where am I? I gotta say, we've been kind of debating because we keep getting lost and asking people and of like, okay, why are we getting lost? And it's by design. Known thing, right? Casinos build no windows, no clocks. It's a maze. It's all intended to keep you inside the ecosystem to incentivize you to play and spend and have fun. And we were just debating about, how far do they take it? And so we did a little research and we learned some really fun facts. These carpets in here are meant to keep you energized. They are zigzaggy, they're colorful. Anytime you walk around a casino, take a look. The tile is always quite busy. It is meant to keep you awake. The lights, the sounds, those are obvious, right? But the carpet was something I did not realize they do. There was even a point where there's subliminal messaging in some of the slot machines where it's meant to get you confident that you're going to win, to give you that little, you can't quite see that they just showed you a jackpot, but your brain kind of picked it up. So with that, I'm going to transition to what does AWS do to keep you entertained with the features that they provide. Now, they have different incentive structures. They're not meant to get you to spend as much money as possible. They are trying to build features for you all to be successful in delivering the things you need to do. But it is a lot of information. It's a lot of signals. It's a lot of things trying to get you excited about new features and trying it out and learning the things. And how do we maximize all of those things? So today's talk is a little bit about engineering practices, but also things we do to also drive behaviors of engineers as well, because we also try to keep our users entertained and ultimately drive action of efficiency. Because when you are so focused on the features and delivery, it is very easy for the cloud to get a little out of hand from a cost perspective and inefficiency perspective. So we'll talk about traditional compute, but in order to get on stage, we needed an AI component in there as well. So we'll talk about GPUs and what we're doing there as well. So we'll click on that. But before we do all of that, who are we? I'm Jersey. This is Brent. We're from Capital One. We lead the FinOps organization. We build tooling. We drive architecture practices and standards. We arm twist and we bribe different folks around the company to do the things to be more efficient, drive the savings, take those savings, reinvest them into other cool features and services that we offer our external customers. And why are we here? How did we get the 4 o'clock slot on a Thursday? Let me tell you, it is because of our rave reviews from our internal customers. As you can see, just the 5 stars across the board of how amazing our products are inside Capital One. I did maybe tweak that last one to get 5 stars. But in all seriousness, we have tools that we build to help users make the right choices. Is your workload efficient? What can you do to be a little bit more efficient? And ultimately, we have 14,000 tech associates at Capital One. And, an outsider telling you that you're not doing something perfectly is we typically have our internal customers on the defense. Our developers are a little bit defensive to say like, whoa, my thing is perfect. I'm definitely doing everything the way it should be. Your tool is wrong. Or maybe not in my case, it might be in someone else's case. So we'll talk about today in this talk around everything we try to do to build confidence in our recommendations, to provide context for how our recommendations are meant to be leveraged for that local team to make that ultimate decision for how they can make their compute more efficient, more effective, and for them to be able to action these things with confidence, and ultimately to have a good experience and give that 5-star review at the end that somehow they keep forgetting to come back to our platform to give us that 5 stars. We're working on it. We have our product manager group here. They're actively trying to bribe folks for those 5 stars. So a little bit about the agenda. We will talk a little bit about traditional compute, kind of how we think about that, and then we'll pivot to to GPUs. These lights are blinding, so if you do have questions, and because it is a packed house, I think let's definitely promote questions during the sessions. So just wave, and then I think I will see you. So we'll stop and take the time if you have anything specific as we go through. 2 seconds about Capital One. We started our cloud journey in 2016. We closed our last data center in 2020. The culture of Capital One has always been data-centric. Even the origin story for Capital One is how do we leverage data to provide a more customized card product to our customers. Fast forward, we have really leaned in on how we leverage modern techniques for driving the best feature sets for our customers. So we heavily invest in our tech that we provide, 14,000 tech associates, and our group here is focused on the efficiency of that. So a little bit about our tooling, just to give you a context of kind of the world we live in. We have a tool that helps you visualize what are you spending on. You're able to kind of look at that data 6 ways from Sunday. But we also, the more complex and I would say a little bit more fun aspect of our job is looking at your utilization and what we think you could do a little bit better in order to be more efficient. So we help provide context about where your spend is coming from. We try to provide context about where maybe the efficiencies opportunities are, because we don't mind you spending on the cloud. That provides value. We really just want to reduce the waste that might be occurring in the system. So we help provide context with data to support recommendations. And then we do other things, which I'm going to put in the cultural incentivization spectrum of how do we gamify, how do we provide metrics that our leaders can look at 1 or 2 numbers to kind of give a trend of how we are doing as a company, as a division, as a team, and then how do we leverage that to get people really passionately trying to do their best so they can say they're better than their neighbor. Kind of the incentive structures. That is also where I introduce cupcakes as bribes to say, look, if you come to our platform and do these actions, a cupcake awaits you. So that is a frequent strategy that we employ. For optimizations, really quickly, we often think about infrastructure. That is the most common thing people typically correlate with efficiency. FinOps efficiencies, right size, use the right instance. We will talk a lot about that still, but it is not just about the hardware. It is about looking at the entire stack, looking at how your code is written, what libraries are you using, what languages you're choosing. Of course, the architecture, more monolithic versus microservice, et cetera, et cetera. So we do think about it through the full stack lens, and we keep investing in our tooling to be able to look at all of these aspects to drive efficiencies. So with that, we will kind of get now into the more data-centric, where this is Brent's expertise of our data guy about how we think about measuring efficiency.
So I guess just from our perspective, going through those 3 layers that we saw on the previous slide, you have the infrastructure layer, you have the platform layer, and you have the application layer. In order for us to be able to get our development teams to be able to do the right thing, we have to be able to build confidence. So just as we start to be able to walk through each of these layers, I'm just going to give you a little bit of background on why we're doing what we're doing and how I'm hoping it's actually building confidence with our engineers to be able to help do the right thing along the way. So at the infrastructure layer, and we could talk about from storage or networking, but just for right now, I think the thing that most commonly comes up when we talk about optimization is, can we actually optimize for compute? So what we did is we went ahead and we said, in order for us to be able to start to figure out what EC2 instances, for example, would a certain application work on, we needed to be able to have a very consistent way of actually measuring the performance of each of those EC2 instances. We settled on CoreMark as a baseline benchmarking. We did it for a couple different reasons. For anybody that's not familiar with CoreMark, and I imagine it's probably very few people that actually are, CoreMark was developed several years back from an Intel perspective, a AMD perspective, and other silicon manufacturers. They each had their own way of actually measuring performance. So in order to be able to kind of get the universal view of what is good performance, they came together, formed what they call the EEMBC. It's just a consortium that they could go through, kind of align on tooling, standards, methodologies. What I like about it is CoreMark's been widely adopted across multiple different clouds. So if you would happen to be able to go to another cloud provider, maybe one that starts with A or one that starts with G, you could actually look out on their website. I can't remember what they are off the top of my head. But you could actually take a look at their website and just see how they benchmark performances. So if you wanted to be able to see in a multi-cloud or a hybrid cloud situation, like the benchmark on-premises versus, very easy to do using CoreMark tooling. The other thing we're going to talk about it here is CoreMark can give like a composite score. It also then starts to be able to get granular. It takes like 9 different operational types, just that you would typically see within an application, and goes ahead and scores those individually, just so if your workload has a certain signature, you say, oh, it performs really, really well for this one, maybe not so for that one, or just in aggregate, here's my overall performance. So we did this across our entire fleet. So in doing so, it allowed us to be able to kind of tease out a couple different observations. Let me step through some of these real fast. Okay, so this one is interesting to me. And I'm not sure how often you deal with it. I know we have the conversation all the time. I need a bigger instance. I need a bigger instance, I need a bigger instance. Our answer more often than not is, first, can we start to be able to use smaller instances and horizontally scale? Well, it's not just always a cost aspect. It starts to be able to get a performance aspect also. As we scale to larger and larger instance types, we could actually see that we tend to be able to lose performance as we step up in sizes. There's a reason behind it. Just behind the actual virtualized instance, you have physical hardware. That physical hardware has boundaries. So as your instance grows, you cross things, we'll say like the NUMA boundary, or you cross physical limitations on a motherboard. So by the time that you actually scale up to full size, you see performance degradation such that you're getting probably 25% less performance per CPU than you did on the smaller instances.
Yeah, and that's a little bit about that trust aspect. So if we're only coming to you every single day, you can be more efficient, you can be more efficient, the app team is going to say like, well, I got to be resilient. I got to meet my benchmarks for like what my app needs. This CoreMarks and the data behind it allows us to be a little bit more intelligent to say like, well, it's not just about the dollars. We actually want you to run a little faster. We have you run into ICE errors because you're trying to get 500 48 XLs. Well, if you actually make them smaller, you horizontally scale, you introduce a higher probability that you're not going to run into ICE insufficient capacity errors for instances. So all of a sudden, we can start thinking a little bit not just about financial efficiency, but we can help the app team think about how they can improve the performance of their platform.
Yeah. We could say it's infinite capacity in the cloud,
yes.
But the truth is I think they run into the same bin packing issues that everybody else does.
Yeah, infinite capacity that hits ICE errors from time to time. It's kind of like the Titanic. It doesn't sink no matter what, ever, whatsoever, except when it hits ice.
I like the analogy. Okay, so here's another one. And so this gets to part of a conversation that I had yesterday. So one of the discussions that we typically have is, hey, can you try to be able to get to the current generation or maybe like one generation behind? One of the objections that I heard was, well, the new generations are actually more expensive. True. If you were to be able to take a look at like a C7 something versus a C6 something, you're probably going to pay a little bit more. However, you have to be able to add the context to that. Each generation has a performance step up from the previous generation. So if we take a look on this one right now, the C8s versus the C6s, you actually see up to a 50% performance boost on the current generation as compared to like N-2. So adding that additional context for I'm getting X amount of performance for X amount of cost is a real powerful motivator for trying to be able to do the right thing.
Yeah, but it's really important to provide that context because folks, if they just hear go to the newer generation, they will pay more if they keep the same size of instance. So really what we want to make sure what they're thinking about is like, well, go to the newer instance, or hopefully we're really trying to work on automating that so we just shift all folks to the newest instances, but then leverage smaller instances. So downside, you downsize them, get the savings, but ultimately still improve your performance as you can see with each generation.
So this next one, and once again, just reinforcing different things that we took away from a CoreMark perspective. is a lot of times if we have application teams go through, change instance types. They say, hey, my application does not perform as well on this particular instance type. I don't know why that is. So using a tool like CoreMark, if not CoreMark itself, allows you to be able to go through and say, hey, what types of functions are you actually running within your application? So depending on the libraries you're using, the functions you're performing, you're going to find that there is a significant difference between processor type, generation. You could even go down to like some of the underlying hardware, like memory architecture, like L1 through L3 cache, that will make all the difference in the world for the performance for the types of functions that you're executing.
Yeah, and as you think about being on one instance or the other, and you might be running hot on one or the other, so there's an operational benefit, there's a financial benefit if you get to the right instance selection, but there's also a sustainability benefit. If you're able to get to the right instance that provides you the value, the speed, the performance, you're able to now potentially be more efficient in the carbon that is being created through the electricity that runs through the machine. So that is additional context that we're layering into our tooling and our interactions with developers to help them not only be thinking about cost efficiency, the performance, the resilience, but we also want to introduce a sustainability perspective to help users take pride in their work, because ultimately any developer can turn on an instance, and if we can create a grassroots movement about getting folks excited about sustainability and leveraging our tools and the data that we provide, it becomes a win-win situation. Because it is, the cloud ultimately federates the controls to anyone being able to make a decision. So we need to take different approaches for different folks that are incentivized by different things in order to maximize the value across our full fleet.
So that was the infrastructure layer. So let's move up the stack a little bit. Now, just full disclosure really fast, just since we've got a huge audience.
Huge. Oh my God.
I wanted to be able to say, like, when Jersey and I were talking about what slides to be able to include, we actually heavily debated this one. Depending on the audience, there is nothing that would promote a fist fight faster than a debate in amongst which language is the best.
I don't know, spaces, tabs?
Yeah. So showing something like this is akin, depending on the context, to calling somebody's baby ugly. That's not what I'm doing here. So as we start to be able to move up the stack, what we're really trying to be able to do is just say, hey, be aware of some of the nuances that different languages, OSs, et cetera, may provide. We had a situation, I want to be able to say, maybe 6 months, 9 months back, where we had a team take their ETL process, they moved it off of EC2 instances, moved it over to Lambda functions. They had the expectation that they were going to save a ton of money. They came back to us and they're like, no, we're actually spending more. This serverless thing won't save us money. So we're like, okay, give us more. They said, well, it doesn't matter how much memory we add to it. We cannot get the thing to be able to run faster. I said, okay, that doesn't sound right. So we take a look at it. So okay, what libraries are you using? Well, we're using pandas. Well, when you dig into the library itself, so pandas is actually based on a Python architecture. Well, for those of you guys that have worked with Python, you know that it's limited in most cases to executing through a single CPU. So as this team was going through and adding additional memory to be able to go ahead and speed up the processes, it didn't matter, because no matter how much memory they added to it, their execution was bottlenecked by a single CPU on the back end. So what we were able to do in that case, so we know that Python or Pandas has a really nice analog in a library called Polars. Polars is actually written in Rust. What that allows us to be able to do is then engage multiple CPUs to be able to parallelize their efforts. Parallelize?
Yeah, sure.
So net result of that, by going ahead and actually now not being bottlenecked by a single CPU, is that they were able to cut their execution times down by 50%. And in a Lambda world, a serverless world, that cut their cost by 50%.
Yeah, and this was just such an awesome example of, it wasn't the infrastructure, it wasn't the architecture, it was which library they used, which ultimately was dependent on what language was that library written in, which was the bottleneck, and that was limiting you to one CPU versus the parallel threads that were allowed through Rust. So something, and funny, we showed this slide with a bunch of distinguished engineers on a call, and somehow we couldn't get off the slide because then they started talking about, well, should I rewrite my entire thing in C or Rust? Which language is best? And really, that wasn't our intent. The idea, though, is decisions have impacts, and as an engineer, be mindful of those decisions. It doesn't necessarily mean that you need to rewrite your entire application. In this example, given the only thing that was changed is a single library in a much broader code base that was processing data. And learning that we then multiplied and looked around other places where folks were doing large data processing and noticed that others were using that library and made that swap. So the idea that infrastructure is the only knob and lever you can twist and move around efficiency is just one component. It can, if you write code that runs in circles, that infrastructure, no matter how much you tune it, will continue to be inefficient.
So once again, kind of moving up the stack. So we're at the final level, the very top of the stack here, at the actual application layer. So just in the same vein of trying to be able to build trust in amongst the development community, in order for them to be able to do some of the things that we really want them to do, not just from a cost optimization perspective, but from a performance optimization perspective, it's trying to be able to build trust. Trust in this particular sense is trying to be able to view the applications through the eyes of the developers. What do the developers care about? More often than not, they care about the resiliency. Does my application run? Does it run without errors? Is my user experience good? So in order for us to be able to go ahead and make sure that we're talking to the developers in the same language that they care about, we had to be able to change some of the concepts that we were conveying. So basically boiling it down to two very simple concepts, and then everything deconstructs from that, is we look at it in terms of load and pressure. Load is how much can we actually put onto the application, how many sessions, how much throughput, how many users. And then pressure, on the other hand, is at what point do we start to introduce latency, errors, and other artifacts that would actually degrade the user experience. So looking in that vein, so I had an example. So we were working with a team, just for context, that was deploying services on Spark. So they came in, and I think they were like, I want to be able to deploy this on a 2XL. So, okay. So they go back in, deploy it, then they come to us, that won't work at all. Why didn't it work? Well, my CPU utilization shot straight up. We need to be able to deploy this on 4XL, I need more. So came back in, no, that didn't work. Well, why didn't it work again? Well, my CPU utilization shot straight up. I'm gonna need an 8XL.
Or some GPUs, maybe.
Just some GPU. So this game continues. So finally, you're like, okay, this just doesn't sound right to me. So we start to be able to take a look deeper into the actual telemetry data to be able to see what's going on. Well, sure enough, if you take a look in aggregate, just strictly from a utilization perspective, their CPU utilization was 90+%. But now we go for the context, actually taking a look at the saturation and errors perspective to see what's exactly going on. Well, of that CPU utilization that was over 90%, 89% of that was sitting in I/O wait. So yes, your CPU is fully pegged or almost fully pegged, but it's doing nothing, it's just sitting there. So then we start to be able to kind of pull on that thread a little bit more. So what exactly is the bottleneck? Well, in this particular case, the bottleneck was actually a logging function that the CPU was waiting on a response from. So the application itself continued to be able to throw more and more and more horsepower to be able to accomplish a task, when in reality, the issue is something downstream. So when we talk about trying to be able to build trust with our developers, a lot of times it requires us to be able to go ahead and kind of take that deeper step into the metrics, into the telemetry data, into the actual traces to be able to see what's going on, to be able to help them maybe decode certain functions within their application.
Yeah, absolutely. So we've spent a little time on compute. Traditional compute. Let's maybe pivot over to GPUs. So as we think about GPUs, the story is not drastically different, but under the covers, there's quite a bit of different things that we're looking at. What's different is instead of application code that we've had now more experience to learn kind of where to look and how to work through those challenges. We are now looking at different models that are being created. Is the right model being selected? How is it being written? What dependencies are being created? We need to be more mindful of performance where, right now it's a rush to market with many feature sets around AI capabilities. So how do we balance the act of driving efficiency with how we leverage GPUs, but also allowing the tech teams and the business teams to drive forward as fast as possible to prove value of these capabilities. The race is on across the industry for who can leverage these new capabilities and tools to provide value for their customers and for their business. So we look across similar types of themes, but we need to now look slightly through a different perspective. So let's talk about maybe GPU availability. If we could switch to the next slide. GPUs are still somewhat scarce. It's not quite the scale up, scale down that we have in traditional compute. So it needs to be considered. And when we consider it, folks might over provision in order to get the GPUs. And then it might be a little bit of a harder job to be able to release those GPUs because you don't know when you will get them back. So as an example on this slide, what we're showing is we might have several clusters where some clusters are running hot while others are sitting idle. And what we have been working with our ML AI team is around, well, how do we reallocate maybe GPUs within the walls of Capital One, but across the different clusters that support different capabilities to be able to provide that appropriate capacity where it provides value, and then maximizing efficiency versus potentially cluster E requesting an additional net new GPUs to the ecosystem. So something that we wouldn't necessarily provide as a solution in traditional compute. We would very much focus on how do we auto-scale, how do we think about those perspectives. And here we're doing a little bit more traditional capacity management and you can call old school bin packing in a way of moving GPUs to where they need to go.
I think in this particular case, it would be all too easy to go ahead and say, hey, let's just create a brand new ODCR, capacity reservation, continue to be able to pay a tremendous amount for instances when, in reality, we could just take a look at what's currently on the floor today and reuse some of that capacity or redistribute the capacity where it's actually needed. Okay, I'm going to get to my favorite one here.
Yeah, this is
if I had a favorite slide, this would probably be my favorite slide right now. So as we were taking a look at GPUs, I liked it because it is a total paradigm shift from what we used to be able to see in traditional compute. I think in traditional compute, if you take a look at the workhorse, you're most likely going to say that's probably the CPU. Every instruction set that's going to be executed on the VM runs through the CPU. Now, when we start to be able to switch context and we look at, how do we measure efficiency in a new accelerated computing environment, that changes. Now, all of a sudden, instead of the CPU actually doing the work, the CPU is responsible for distributing the work to the GPU. Now, that unto itself, the GPU doesn't actually do the work. What the GPU is comprised of is a whole lot of streaming microprocessors. So that work is actually based on how heavily you're able to go ahead and utilize those streaming microprocessors, or very specifically the CUDA cores on those microprocessors. That's a lot of information, but basically saying, hey, the paradigm that we knew in a traditional environment doesn't exist here. So we have to be able to change the way that we look at the world and measure efficiency.
Yeah, if we just leverage the same telemetry that we use for traditional compute, we could look at the CPU usage, see it's at 2%, go to our AI ML team, start yelling at them saying, hey, your CPUs are sitting idle, and they'll look at us and say, yeah, but the GPUs are running. So we need to look at different telemetry for us to have the context in order for us to provide a kind of an intelligent opinion about how efficient you're running your GPUs.
So if you were to be able to go through and we'll say like provision a P4D 24XL today, what information's available to be able to help you actually make an informed decision on utilization? There's three different markers that you could take a look at that would help kind of narrow down what you're seeing. The very first one would be temperature, like actually taking a look at the thermals off the GPU. Second one would be the wattage draw. The third one is utilization. In a CPU world, you can take a look at utilization and you get a measure for how many of the resources on the CPU would actually be used. In a GPU context, the utilization only refers to like for what amount of time were any of those streaming microprocessors, or more specifically CUDA cores on these streaming microprocessors used. So basically utilization, while not a meaningless metric, means something different in a GPU context. So how do we measure it? What we do is we know that each and every one of the GPUs has its own specification for maximum wattage, for its own like maximum thermal readings. So we have to be able to go through, we take a look at what's coming off of the GPUs itself for any given period of time, and then measure that in context against the maximum that it's actually rated for. So in this particular example, we could take a look at the, we'll say the very top one. I'm just going to make it extraordinarily simple. We'll say the actual GPU power usage for the A100 would be 175 watts in this particular case. If we know that the maximum, I believe is higher than this, was 350 watts, we could say, okay, you're only using 50% of the resources. So context is everything. For if you were to be able to boil it down to a simple equation, take a look at the actual power usage divided by the maximum wattage threshold per GPU.
So pretty much when we say it's running hot.
Running hot.
It's running hot.
You're efficiently using the resources.
So so we know we can get access to CPU telemetry. How do we get access to power? How would one get access to this?
So this actually comes natively within the current AWS metrics. So DGIM from NVIDIA in this particular case automatically outputs the metrics, so you're able to ingest these through your regular flows for measurement.
Awesome.
So I guess in the same vein of context being absolutely everything. So taking those very same measurements that we just looked at to be able to say, hey, how efficiently are you using resources? And you could start to be able to form some extraordinarily interesting observations. I guess in the example right here. So picking on the same, we'll say like A100, we know that more or less there should be an extraordinarily strong linear correlation between utilization and wattage. While it's not 100%, it should be fairly strong. What's interesting here, if you take a look at it, is going to be that bottom right-hand corner where you see the circle. You're going to see a number of examples of where you have readings of where the utilization starts to be able to spike, but the wattage doesn't rise at all. What that tells us is there is a resource on that GPU, maybe a single microprocessor, maybe a single CUDA core that's actually being consumed, but it's not doing a lot, and you're not consuming all the resources on that GPU. So in essence, like this is a loss of efficiency. So this for us could mean a number of different things. Could mean that there is a structural problem with the workload, structural problem with the model, or maybe a way that the actual environment's being architected is prohibiting users from using all the resources they're currently paying for.
Yeah. So, I mean, at the end of the day, we can't give the precise answer in this case. This is a learning journey that we will only get more and more insights with experience. But it allows us to go to that team that is building the model, that is running the model, and for us to provide them indicators to say, you might not be running as hot as you think you are. You might be able to get more out of your compute than what you think your limits are, and here's some data to support it. Let's work together towards kind of taking that next step. So, you know, certainly we're not in the as precise area as we are in traditional compute, where we can quite more easily pinpoint the problem that is driving the utilization efficiency mismatch. But it is certainly helpful to be able to indicate that we're not at destination. We need to take a look and then maybe rerun this and then see what the benefits we get by potentially changing things up at the app layer.
Like, I'm a big fan of oversimplified versions of the world. So this right here, while it's definitely an oversimplification, this just basically provides a structural context for how you could potentially take a look at what you're seeing based on telemetry that you ingest, and then be able to decode what you actually have going on within your environment. So, like for example, if you see, we'll say, I'm just going to walk through this really fast. We'll say like high CPU utilization, but everything else shows really low. That shows that the CPU's setting a whole lot of task requests to the GPU, but the GPUs are underutilized. That tells me in this particular regard, I need to be able to go back, if I'm running a model, re-architect my model to be able to provide like larger chunks of data to be able to fully utilize the resources on the GPU. So this would just be like one example of how to be able to look at it. So as we start to be able to go forward in this brand new accelerated compute instance version of the world, it's building just ways to be able to have like a decoder to be able to better understand what sort of things are happening within your environment.
I got nothing.
Okay, so I guess bringing it all together. So coming back like to the very beginning, we started to be able to talk about like 5 stars as always, which is what we strive to be able to deliver. It's really trying to be able to understand for the user base that we're serving, what are we trying to be able to do to be able to help them? What can we do to be able to actually serve their needs rather than our own interests in this case? So it's developing a deep understanding of what's actually being done within the application itself and how we can better address those. For us, and Jersey mentioned we got our product management team here, we tried to be able to take some of those learnings, those key observations back and make sure that we incorporate those into our tooling. So everything that was super interesting we talked about here, we try to always make sure that we're actually surfacing a view of that information so when our teams go into our tooling, they can start to be able to develop those same insights. And at the end of the day, like a lot of this is extraordinarily deep. If we were to be able to go through and try to measure everything, we basically effectively measure nothing. So it's picking out what are the few key things that we can start to be able to bubble up to the top that are going to have the most value for the teams that we interact with.
I think you missed one. There's one more. So I think the most important thing that you need to get out of this is rugs that are being chosen by other people are there to manipulate you, and don't fight back. If you see a very busy color scheme in your office, that is your employer trying to get the most work out of you. So fight back, and remember, and by fighting back, you do that through driving more efficiency. Think of us. Think of us if you see ugly carpet and what you can do to be more efficient. So I hope you enjoyed the closing remarks here of reInvent 2024. I believe we're live streaming. I'm seeing 2,000 people listening to us from Venetian. So thank you all for joining. If you have questions, we'll be here for 15 minutes until our happy hour starts, and then we got to go.
Thank you, guys.
Thank you.